Now if f of t is a periodic function with period capital T, you can find its Laplace transform by finding a transform on just the interval from 0 to t, multiplying by 1 over 1 minus e to the negative s times capital T. Capital T here, capital T here. The idea is, if you have a periodic function then, you just have to look at the Laplace transform on one period and then divide it by that 1 over 1 minus e to the negative s times the period. And we saw where that arises previously looking at just a step function. It generates a geometric series in e to the negative ts, and this is the sum of that infinite series. Okay, so we're going to consider sawtooth on the interval 0, capital T, and we're going to give it something like an amplitude. It's not really going above and below the axis. We're just going to repeat this period of the sawtooth. We could do it where we have a period that goes from here to here, down, and then back up, which would be a lot like a sine wave. And that one actually would end up with a much nicer Fourier transform. But we're just going to transform this just as an exercise. Okay. So we see that between 0 and t over 2, we have a run of t over 2 and a rise of a. And then between t over 2 and t, we have the negative of that of the corresponding slope. Slope here then is a divided by t over 2. Slope here is the negative of that. So we have slopes of these two segments are plus and minus a divided by t over 2 plus or minus 2a over t. We just use simple precalculus to get the equations, piecewise equation, our formula for the function. And now we integrate that function from 0 to infinity. But of course, everywhere except from 0 to t, the function is 0. So our integral from 0 to infinity of f of t e to the negative ts just becomes the integral from 0 to t of f of t e to the negative 2s. Plugging in the piecewise definition of our function, we have the integral of this function from 0 to t over 2, that's here, and the integral of this function from t over 2 to t, that's here. We separate the two terms that we get in this integral because we have two different, we're going to use two different integration techniques. We get the 2a times e to the negative ts here. That's, of course, integrated from t over 2 to t, the same as this is. And we get the negative 2a over capital T times t e to the negative 2a ts, small ts. Again, from t over 2 to t. And over here, we have this. Now we notice that this integrand is the same as this integrand, but we have different limits. This integral goes from 0 to t over 2, this from t over 2 to t. I was in hopes that somehow this would kind of cancel out what we get when we substitute the upper limit here with when we substitute the lower limit here. But if you think about it, that's not going to happen because you've got a negative sign here. You might want to think through that. Something I should have thought through when I did it originally because I made some mistakes. Okay. So this integral, well, we do the antiderivative of t e to the negative ts, which I did in my head and messed up, finally fixed. There it is. And actually, over to the right, you see the partial fractions decomposition. There it is, and you can do the partial fractions. That's easy enough. So this integral, when you substitute the lower and upper limits, well, the upper limit, t over 2, going to substitute t over 2 for the t here and the t here. So we're going to end up with a t over 2 here and a negative t over 2 here. Okay, now I'm not going to point out all the details of that, except to say that when we do this integral, we'll be substituting the t over 2 as the lower limit, and that's going to be here. Okay? But we're subtracting this integral, so even though this looks like it maybe ought to combine with this to give us 0, it doesn't. It actually gets double. Okay, because we have two negatives here and another negative. So we're going to end up with a negative on the 1 over s times this mess, and we have a negative here. So it's nothing's going to go away. Which is, of course, what you always hope when you get something that's a little bit messy. Well, we just go through the details and write the integral down. And at the end, in class, I attempted to put this into some kind of coherent form. And there are more coherent forms than what we have here, but there's none that's really going to be all that helpful. What I would do at this point is I would take these terms and group the ones with the 1 over s squared, okay, especially the ones with the 1 over s squared e to the negative ts. You've got one here, you've got one here, I'm sorry, negative ts. You just got one here with the 1 over s squared. And that's the only one you've got with the 1 over s squared with the negative ts. So negative t over 2 times s, e to the negative t over 2 times s, you've got a 1 over s squared here, 1 over s squared here. You've got to combine those, be careful about your signs. It's a negative of a negative, and a negative of that. So they're going to reinforce, as we said before. Then maybe the 1 over s squared e to the negative t term, there is one there, e to the negative ts. And then the negative 1 over s terms, and then all the terms have at least a negative 1 over s. So it's a little messy, and then you get to divide it by 1 minus e to the negative st. And then you want to inverse transform it. It's a little more than I'm going to actually ask you to do in this course. We're just touching on Laplace transforms a little bit to give you the basics, the very basics. I certainly expected to inverse transform a lot of other things, but that was going to get a little hairy. In any case, what you end up with is Laplace transform of f of t is the integral from 0 to t f of t e to the negative ts dt, which is all this, in this case, divided by 1 minus e to the negative ts. Okay? So, that's pretty much it. Pretty much it. You want to see how we get Laplace transform for periodic functions, because a lot of times you're driving a circuit or a mechanical device with something like a sawtooth or a step function or some other periodic function. It's not nice like a sine or a cosine. If you're driving a system with a sine or a cosine function, you can use things like variation of parameters, undetermined coefficients to solve the non-homogeneous equation. With Laplace transforms, you just transform the whole blamed equation and find the expression for the Laplace transform, inverse transform it, and there's your solution. So it's kind of neat, but it's also necessary when you don't have nice smooth functions.